All right. Oh, let's see now. Let's try it again. Hey, Julian. Let's see what's. If you're talking, you're muted. Oops, too far in again. Let me put where's my chat? There we go. All right. Don't forget to put your name in chat. And I'll be right back. I'm gonna run ever since I got here and had a chance to. Even though having diabetes is not fun. Turn that thing off. Okay. Well, that's okay, Julian. No, Julian's not in the room anymore.
Where is he? I can't see. Let me see. But gallery. There we go. There you are. Okay. You weren't showing on my screen because I had it set different. And I apologize. It's taking me a little bit to get things going again this morning. So oh yeah. Let's see, get this turned on. Thing. All right, I got to sign in. Before you leave, be sure you initial by your name at the appropriate column. Let's see what else. Okay. I'm trying to remember where we left off last time. No, that's not what I want. Why is it doing that? Did it just put a link? Yeah, it did. It just put it a link. I thought I had downloaded the PowerPoint to the computer, and I had not. So let's see. Let's see how that works. This is why I get here at 7:30, so I don't have to take up 10, 15 minutes of last time to get this thing running. Waiting for the PowerPoint to come up. There Have we gotten to the even odd properties of the trig functions? Anybody remember?
I think the last thing that one was like identities.
Oh, okay, we're still in the end. Okay. So we had we. It was working. Good. All right. So did I? Had we had already covered all of this? And talk about how to derive them. And these are the fundamental identities that we went over. These are kind of your go-tos when you're doing trig identities to try and see what's going on. If you're on Zoom, you need to pin my screen so it's the biggest thing there. And so you don't have to squint to see it. Because I have a pretty big screen here and I can't read that. So, okay, let's see if this is working. Yeah, all right. And so we can find these exact values without using a calculator. Okay. I felt like we did this slide. So if I remember correctly, this wound up equaling cotangent 40. So we're subtracting cotangent 40 minus cotangent 40, which gave us 0. And this one, 1 over cosecant, if we look back here, is it cosecant? Yeah, cosecant is 1 over sine. So sine is 1 over cosecant. So this is 1 over this is 1 over sine squared. So we have sine squared plus cosine squared, which gives us 1. When they're the same angle, when you're taking sine and cosine of the same angle. So did we do this line? Okay, we'll do this line. Okay, given that the sine is, okay, yeah, I did this one. I remember doing this one. I do it my way and the textbook says they have a better way. Okay, so sine is y over r. Okay, when you don't know what the radius is, okay, when we first introduced this, we said that sine theta equals x, but that's when the radius was 1, because we were talking about the unit circle. Now we're not talking about the unit circle. So since sine equals 1/3, then that tells me that x equals 1 and the radius is 3. Right, and they're telling us that cosine is negative. Well, if we look at the quadrants, and we want to know where sine is positive, because they said it's 1/3, not a negative 1/3. So here, everything is positive. Here, sine is positive. Down here, tangent is positive, and here cosine is positive. So knowing that situation tells me that this cosine is going to be negative, or cosine is going to be negative. So that means tangent is going to be negative, because we're talking about this quadrant up here, right? Where sine is positive and cosine is negative. So sine and cosecant will be positive, and the rest of them will be negative. All right. So now we have the fundamental equation for a circle when it's centered at 0. And we know what. Oh, no, not x, y. I'm sorry, I misread what I wrote up here. We have y is 1, so 1 squared is 1. So we have x squared plus 1 equals r squared. R is 3, and 3 squared is 9. And so we get x squared equals 8, or x equals the negative square root of 8. Okay. Because we know x has to be negative because of which quadrant we're in. And we simplify the radical. Well, this is negative square root of 4 times 2, and the square root of 4 can be pulled outside, so it's a negative 2 square root of 2. So now we know cosine, and this, cosine is x over r, so this is a negative 2 square root of 2 divided by 3. And we know tangent. There's a couple of ways to deal with tangent. I can say tangent is y over x, or I can say tangent is sine over cosine theta. But doing y over x would probably be easier since we already have those numbers. Y is 1, and the denominator is a negative 2 square root of 2 over 3. And this is just saying we want the reciprocal of the denominator. So this is going to be a negative 3 divided by 2 square root of 2. And we multiply by the fraction square root of 2 over the square root of 2. So we rationalize the denominator. And we wind up with a negative 3 halves, right? No. A negative 3 square root of 2 over 4. Because square root of 2 times square root of 2 is 2, so my denominator becomes 2 times 2. And doing it this way, you just have a more complicated fraction to deal with. You're going to be multiplying 1/3 by the reciprocal of negative square root of 2 over 3. Uh-oh, I did that wrong, didn't I? Because I used this instead of this. So there isn't a 3 down there. So there isn't a 3 up here. So this is just 2 square root of 3. I mean, it's negative square root of 2 over 4. Yeah, we don't want it. Now this one would have the fractions involved. The 1/3 over negative 2 square root of 2 over 3. And then you do the reciprocal of negative 2 square roots of 2 divided by 3, which is the 3 divided by negative 2 square root of 2, and you multiply that by 1/3, and the 3's would disappear. And then you would rationalize the denominator, and you'd wind up with this thing here, and you rationalize the denominator and get that. And then the other 3 are just reciprocals of what we had. Cosecant is a reciprocal of sine, so that's going to be 3 over 1 or 3. Secant is going to be the reciprocal of a negative 2 square root of 2 over 3. And that works out, that's the one I've done. The reciprocal of that winds up being 3 square root of 2 over 4, and it's negative. So this is what secant winds up being. And then cotangent is the reciprocal of tangent, but I'm going to do the reciprocal of this fraction here. And so cotangent becomes a negative 2 square root of 2. Okay. Oh, Sebastian, no, the weekend hasn't been mine, and I finally, I think I downloaded I created the PDF files, but I don't think I uploaded them to every to the class yet. Someone had asked that they still can't see the numbers and stuff on the slides. So on the PowerPoint I put in there. And that has something to do with not having the fonts and or the program used to create the pictures. So that's an expense you don't need. And they went through a couple of ways of doing this, to find these. And, they came up with another way of using this trig identity, which is basically what I did when I first solved this one. Is put sine is 1/3, so that's going to be 1/8. I mean 1/9. And 1 minus 1/9, because we're going to subtract sine squared with that. Oh, and they what they did, they solved the trig identity, the Pythagorean identity, for cosine, and wound up with this, and then just put 1/3 in for sine, and worked it that way. Still wound up getting the same thing for cosine without having to find out what x and r are supposed to be. And then since you have sine and cosine, you can build tangent, and then you have sine, cosine, and tangent, you can build the reciprocal functions. Okay. Sine over cosine, and it gets a little messy when solving this. We would flip this fraction and multiply it by 1/3. Okay. And I believe I've done this one. And then secant is just a reciprocal of cosine, and cosecant is a reciprocal of sine. And there we have the remaining 5. Personally, this is the method I would use. Because in my head, it's straightforward that way, but going back to this, you still end up using the Pythagorean, a Pythagorean identity, but using x squared, y squared, and r in place of sine, in place of the fractions for x, y, and r. Okay. So given the value of one trigonometric function in the quadrant, the exact value of each of the remaining 5 trig functions can be found in either one of 2 ways: using the radius, which is what we did here. Draw the circle, and then then we find the radius using the distance formula, because we're talking about it's being centered at 0. And step 2, assign a value to 2 of the 3 variables based on the value given in the trig function and the location of P. And then use the fact that P lies on the circle x squared, y squared, r squared, x squared plus y squared equals r squared, to find the missing variable. And then the theorem on page 386 deals with the x over r, y over r, y over x, x over y, and the reciprocal functions from that. And then the other way is use appropriate identities to find values of each of the remaining trig functions, which was the second way they did it, which is the way I would normally do it. Okay. So here we know what x and y are. Because tangent, well, tangent is the square root of 3 over 3. So that's y over x. So x is 3 and y is the square root of 3. So x squared plus y squared equals r squared. So we have 9 plus 3 equals r squared, or 12 equals r squared. So that means r equals 2 square roots of 3, because we're going to take the square root. We're going to take the square root of 12, which is the square root of 4 times 3, and we can pull the square root to the outside. So that becomes 2 square roots of 3. And r is positive. Now, we want to know which quadrant we're dealing it in, because now x or y or both x and y could be negative. Right, so tangent, they're saying tangent's positive. Well, tangent's positive in the first quadrant and the third quadrant. So we're probably going to change which quadrant we're talking about from that previous problem. Okay, and sine is negative. Sine is negative in the third and fourth quadrants. So we're talking the third quadrant where both sine and cosine are negative. So that means both x and y are going to be negative. So sine is y over r. So sine of theta in this case is going to be a negative square root of 3 divided by 2 times the square root of 3, which simplifies to a negative 1/2. Cosine is x over r. So cosine is a negative 3 divided by 2 square roots of 3. Multiplying numerator and denominator by the square root of 3, you wind up with the negative square root of 3 over 2. There's negative 3, square root of 3 times square root of 3 is 3, and these two 3's would end up you'd have a 3 in the numerator and a 3 in the denominator, and those would go to 1. So that's what happens there. Okay. Cotangent is just flipping this fraction. So that's going to be 3 over the square root of 3, which winds up being the square root of 3. Cosecant is a reciprocal, and cotangent has the same sign as tangent, so it's positive. And the others are going to be negative. So the reciprocal of a negative 1/2 is a positive 2. I mean, a negative 2. And the reciprocal of cosine gives us secant. But if I look at this fraction for cosine, I won't, excuse me, and I flip the fraction, I won't have to rationalize the denominator. So that gives me a negative 2 square roots of 3 over 3. And that gives us the remaining fractions, the remaining functions. Okay, pin. If you're in Zoom, pin my screen. Okay, and it's still too dark. Let me see. always right reading when I'm writing, but it's not the right lines. Did that help? A bit, okay. Just gonna have to find a black marker. All right, so they went in and did the method I did. And found what those things were. And did the same thing I had done to find the remaining trig functions. And then as a value of tangent is known, use Pythagorean. Oh, they use Pythagorean theorem here, where tangent squared plus 1 equals secant squared. So you square tangent, so I square this, and I wind up with 1/3. Because then I get 3/9, and 3/9 is 1/3. 1/3 plus 1 is secant squared, so 1/3 plus 1 is what? 4/3. So secant is 4/3. Secant squared is 4/3. So the square root of 3. So you take the square root of numerator and denominator, and you get 2. The negative 2 divided by square root of 3. And then you simplify that, and you wind up with this. And cosine, you do the reciprocal of this, which gets you to here, which brings you to here. And then tangent is just the reciprocal of this, which brings you to the square root of 3. Oh, yeah. And then to find sine, they did it this way. So tangent times cosine. Tangent is square root of 3/3. Cosine is the negative square root of 3/2. You multiply. Oh yeah, it comes out to 1/2, negative 1/2. Okay. Which is what we needed to have happen. And cosecant is just a reciprocal, which gave us -2. So even in odd properties of the trig functions, if you remember, even in odd, if a function is even, it has symmetry with respect to the y-axis. This is an important concept from college algebra. So when it's an even function, it's symmetric about the y-axis. And if it's an odd function, it's symmetric with respect to the origin. And if you do f of negative x, then and you get f of x, then that was an even function. And if you did f of negative x, but it came out the negative of f of x, then it's an odd function. And so looking at these, the sign is an odd function, because the sign of negative is the negative of the sign of the positive. So if I had the sign of a negative pi over 4, well, then that's going to be the negative of the sign of pi over 4. So that's going to be a negative square root of 2 over 2. And since sine and cosecant are negative, are reciprocals of each other, then it's going to hold the same property. Cosine is an even function, because the cosine of a negative is the cosine of the positive. So if we did the same thing here, the cosine of a negative pi over 4 is the same as the cosine of pi over 4. So that's going to be the square root of 2 over 2, is positive. And secant is reciprocal of cosine, and it has the same property. And tangent is also odd. Well, it's an even function divided, an odd function divided by an even function. So it's going to be odd. Just how it divides out. So if I have the tangent of a negative pi over 4 is going to equal the negative of the tangent of positive pi over 4. Well, tangent of pi over 4 is 1. And so that's just going to be 1. Negative 1. As we were talking about this angle here. No. Sorry. Because we went negative pi over 4. Which is actually this angle. 315 degrees, or 7 pi over 4. It's going to have, they're going to have the same value of this angle. This is negative pi over 4. And this is pi over 4. So they're going to have the same values, except we need to take into consideration which quadrant we wind up in. Okay. So we wind up in the 4th quadrant here, and sine is negative there, cosine is positive, and tangent is negative there. So sine and cosecant will be negative, secant will be positive, and cotangent will be negative. It'll be the reciprocal of those values. Cosecant will be negative 2. Cosine will be positive 2, and cotangent will be negative 1. All right. Negative 30 degrees. Which will be the negative of the sine of 30 degrees. So what's the sine of 30 degrees? Okay. Negative 30 degrees takes us down here, but positive 30 degrees is up here. So it's going to have the same y, it's going to have the opposite sign of the sine value. What's the sine of 30? Huh? 9. a half. So this will be a negative 1/2. Right. This is going to be the same as the cosine of pi over 3. Right, so a thing here to see is notice which quadrant, where's cosine? Cosine is positive over here. So of course these x values are going to be the same as these x values, where these y values are going to be the negative of these y values, and vice versa. So what's cosine of pi over 3? Isn't that 1/2? Cotangent, that's going to be the negative of the cotangent of 5 pi over 4. 5 pi over 4 is over here. Or negative 5 pi over 4, excuse me, is going to be up here. Because we go this, I always forget about which direction we're traveling. And this is a pi over 4 angle, so it's going to be either 1 or negative 1. Right? Cotangent of 5 pi over 4 is in this quadrant. And cotangent is positive down here. So cotangent, this is a 45-degree angle. And so it's going to be, the cotangent and tangent will be 1. It's just what's the sign? Well, the sign is negative, I mean positive here, but we want the negative of that. So this is going to be a negative 1. This next one goes round and round and round. Okay. So this goes around the circle, this goes around 7 times. Right? Because and I can bring this negative sign out because it's an odd function. So now I'm just going to talk about the tangent of 29 pi over 4. Well, 29 pi over 4. If I write this, taking out the full circles and writing that as one part, so I have 29 pi over 4. How many times does 4 divide 29 evenly? Well, that's the same as 7 pi plus 1/4 pi, because that's 28 pi plus pi. And 4 can divide 28 evenly. And so that's how I separated them out. So that means it went around 2.5 times. I mean, 3.5 times. So the positive angle, we're going around once, that's 2 pi, another time that's 6 pi, and then 1/2, which is 2 pi. 4 pi, that was 4 pi, and then another time is 6 pi, and then another 1/2 is the 7 pi plus 1/4 pi. So that's this angle down here. So this is the same as the negative of the tangent of pi over 4. No, that's 5 pi over 4. And tangent to 5 pi over 4 is 1. So, but we want the negative of that, so it's negative. Yeah, these line up in the same place. This angle and this angle have the same terminal side. Okay. I'm gonna go through them. There we go. All right. Now we're going to start talking about the graphs of sines and cosines. The graph of the sine of y equals sine of x, and the function of the form y equals a, and it's a capital A, sine omega. That funny looking W is an omega. X. And how I usually write omega, which you already may have seen me do it, is something like that. And then we're going to look at these graphs. We're going to determine amplitude and period of the sinusoidal functions. Yeah, that word is pronounced sinusoidal. And but it looks like sinusoidal, but it's sinusoidal. And the graph is sinusoidal using T points, and find the equation for a sinusoidal graph. And is there a second slide to this? No. Okay, what we mean by sinusoidal is they go like this. So it's a smooth, continuous curve that undulates up and down, up and down, up and down. It has a maximum value it reaches, and it has a minimum value it reaches. So it has a local, it has an absolute maximum and an absolute minimum. So for that particular function, it will hit the highest value an infinite number of times. And so that's where the period comes into play. And knowing how high and how low it goes, we're talking about its amplitude. So amplitude tells us about how high are the hills and how deep are the valleys. So you can have another sinusoidal function that that barely has any wave to it all, where its maximum values and minimum values are closer to the x-axis. Yeah, and the x-axis would go through the middle here somewhere. Okay, and if it's a sine function, it would hit here. The y-axis would hit here, and if it's a cosine function, it would go through here. Okay, because sine of 0 is 0, and cosine of 0 is 1. I'll leave the damn thing all the way over here. And what I'm looking for. Okay. So we want to graph trig functions in the XY plane, we use a traditional symbol X for the independent variable or argument. So instead of using the symbol theta, the Greek letter theta, we're going to use X. And the Y value is the Y value you get. So it's a typical XY. And so this is how we write those trig functions. Y equals sine X, or f of X equals cosecant X, or, you know, you either use the Y or the f of X. Okay. So here's a graph of the sine function. Well, we know what those sine values are going around this unit circle. Right? At 0, y is 0, and x is. Okay. So x is the degree or the radian, and 0 is the sine of that angle. So at pi over 6, it's 1/2. At pi over 2, it's 1. At 5 pi over 6, it's 2. And at pi, it's 0. And then when you go to 7 pi over 6, it's -2. And then you continue on. So this is just one period out of the graph of the sine function. See, they limited the range, the domain, from 0 to 2 pi. So when we talk about the key values that they were talking about on this page, graph using key points, then this is what we're going to be looking at, these values here at 0, 1/2 pi, 1/2 pi, pi, 3/2 pi, pi, 2 pi, and then 7/2 pi, and then 3 pi, and then so 9/2 pi, 4 pi. So this just gets moved to here. And so we just dovetail it here, and then we dovetail it again. So it just keeps going back and up and down, all the way down. The highest it gets is 1, the lowest it gets is -1. And it's the period keeps repeating. That's a sinusoidal function. And we call it sinusoidal. We call these types of functions sinusoidal because of the sine function. That's where they get the name from. The domain is all real numbers, but the range consists of all real numbers from -1 to 1, inclusive. The sine function is odd, has symmetry of the graph with respect to the origin. The sine is periodic with a period of 2 pi. The x-intercepts are at the integer multiples of pi. -2 pi, -pi, 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 8 pi, 9 pi, all the way down. So the whole number values of pi is going to hit the x-axis in the positive and negative direction, and it goes through the point 0, 0. Because the y-intercept is 0, and that kind of falls in line with the fact that it's an odd function. Although not all odd functions has a y-intercept. But if they do, the y-intercept will be 0. The maximum value is 1, and it occurs at odd multiples of pi over 2. Odd integer multiples of pi over 2. So negative 5 pi over 2, negative. No, it's not all. It skips every other one. Yeah, because at the odd multiples of pi over 2, it's either going to be -1 or +1. So you just have to figure out where you're starting at. And when I have you graph these things, I want at least 1.5 periods. So you figure out what the period is, and then you figure out 1.5 periods. And those are the key values you're going to look for to graph. A minimum value occurs at those values. And please notice, they're 1 pi unit, or are they 2 pi units? Plus pi. No, plus 2 pi. They're 2 pi apart. A period. So I'm going to go back to the picture. So the next one is going to be the next, if this graph continued, the next where it hit the maximum value would be 2 pi away, 1 period away. And another period away, it'll hit this minimum value. And then so these high points are 2 pi apart, and the low points will be 2 pi apart as well. Yeah, I'm trying to remember. There's a formula for it. Plus or minus 2k pi, or 2 pi k. Yeah. And this one starts at pi over 2. Pi over 2 plus or minus 2 pi k. And this one starts at negative pi over 2 plus or minus 2 pi k, where k is an integer, Or actually, since I put plus or minus, k is a positive integer. Or a non-negative integer, because you can multiply by 0. And you just have that. So this is the pattern for these values. And this is the pattern for these values. If you don't put a restriction of positive or negative on k, you would drop the plus or minus, where k is any integer number, integer value. Okay. All right, so now we have a transformation of the graph. My sine function, f of x equals sine of x, but now we're doing 3 times x to get 3 sine of x. So I'm multiplying each y value by 3. So that's a transformation, that's a stretch, because I'm changing in the y value, so I'm multiplying, so I'm stretching it out. So let me see how we do it. I think my pictures suck. And so I'm glad they're side by side and not on different slides. All right. I wish they would. This looks like it's compressing it this way, doesn't it? That picture. But this scale here has been shoved in. I wish they had it the same distance as that one. All that happened is, instead of going up to 1 here, which would have been here, Now that got pulled up to there. And this one, instead of being at -1 down here, it got pulled down to here. And so that's what happened to all the y values. You multiply them by 3. So instead of being, and this one would have been here. Instead of coming through like this, everything got stretched out. So now my smallest y value is now -3, and my largest y value is +3. That's the amplitude. The amplitude is what you multiply the sine function by. So I'm changing how high it goes and how low it goes. So the amplitude trying to remember, they use absolute value somewhere along in here, but this is, oh yeah, is the absolute value of absolute value here is 3. They say the absolute value of A is 3, so that's the amplitude. And A is what sine is being multiplied by. So the domain remained the same, but now the y values change. So when you're changing your amplitude, you're changing your range. So the smallest it can be is -3, and the biggest it can be is +3, and it's all the numbers in between. So instead of bouncing back and forth between these two values, it's now bouncing back and forth between these two values, the -3 and +3. As x goes in the positive direction or x goes in the negative direction, the y values just keep bouncing up and down, up and down, up and down. Okay. Now I'm not only am I changing this, the amplitude, I'm changing my x value. I'm multiplying my angle by 2, and that's going to be a horizontal, either a stretch or a compression. Since I'm multiplying my argument, my x value by a number larger than 1, it's going to be a compression. So it's going to look similar to this, but it's going to be squashed towards the y-axis. And then this just changes how high it goes and how low it goes, but flips. So where -1, where 1, 0 was on the graph, now it's gone down to -1, 0. So the y-intercept flipped across the x-axis. So what was the first thing they did? Sine, I'm sorry, I thought they were doing cosine. Sine 0, 0 stayed 0, 0. So the first thing they did was the minus sign. So they flipped it across the x-axis. Okay. And then the next thing they're going to do is change its amplitude. So instead of going from 1 to -1, it's going to go from 2 to -2. Okay, so they changed the period. They changed the amplitude. And now the next thing is they're going to change the period because they're changing the angle. So instead of dealing with well, which one did they change? They changed the 3 pi over 2. Yeah. So that would be like multiplying by 1/2 times x. So where the y value remained the same, 3 pi over 2 gets moved this way by multiplying this by 1/2. So instead of being out here at 3/2 pi, now it's going to be at 3/4 pi. Right. So this point got moved back to here. And that's what they did here. And then 1/2 -2 got moved back to to 1/4 -2. And that's how they got this point here. And this over here, pi over pi, negative pi divided by 2 brings this point over to here. And this point got brought half of the way back over to here. 0 stayed at 0. Oh, this one got moved. This one got moved to here. And over here at 2 pi got moved back to here. So the new graph yeah. Okay. I just like to overlay them because I can see it better if I overlay it. Anyway. So the domain remained the same, it's still all real numbers. But the range had changed. Because instead of going from -1 to +1, now it goes from -2 to +2 inclusive. Okay. Now the graph of cosine. Please notice that the graph of cosine and the graph of sine look very much alike, very similar. It's just they have different y-intercepts. Where if I shift this graph half a pi either to the right or to the left, I'll get the sine function. So sine and cosine are just a period shift. And so cosine of 0 is 1, and the cosine of 3 pi, 1/3 pi is 1/2. The cosine of pi over 2 is 0. And so you're just taking that chart you built up from the unit circle and just graphing the angle with the cosine value, just like we were graphing the sine. We're doing the same thing, graphing the sine, the angle with the sine value. So each of these points are, in this case, x cosine x. So that's what's the value of each point on here. So where this is the angle value and this is the cosine value. Okay. And just like the sine function is sinusoidal, so it just bounces up and down, up and down, up and down. Forever, in both directions. The domain is a set of our own numbers. Whoa. It just all of a sudden stopped my. Why did it do that? Here. Okay. I don't know why it dropped it. I have no idea. And so it's an even function, so it's metric with respect to the y-axis. So if we look at the slide that they had previous, here's a y. So these are mirror images. These are mirror images. So if I fold it this way, they'll line up quite perfectly. And that's what they talk about here. The cosine is periodic. It has the same period as sine. The x-intercepts are the x-intercepts, yeah, are odd multiples of pi over 2. Odd integer multiples of pi over 2. Where with sine, it was multiples of pi. And the maximum value is 1, and it occurs at the multiples of pi. No. They got this wrong. Yeah, they got it wrong. So the maximum values are at the even multiples of pi. So at 0, at 2 pi, at 4 pi, at 6 pi, positive and negative. So, oh man. The author here needs to be beaten with a stick. So it'd be the even multiples. So negative pi over 2, 0, pi over 2, 4 pi over 2, and the minimum value occurs at odd multiples of pi. I don't know what that idiot was thinking. he's got too many mistakes in this. And I found out from my dean that this guy's been putting out has put out hundreds of textbooks. And he's been doing it for a couple of decades. So I don't see why he's making any mistakes. Well, he's probably not the one writing the slides. And then graphing this using transformations. All right, so we know what the cosine function looks like. Multiplying it by 2 changes how high it goes and how low it goes. So it goes from -2 to +2. Now I'm going to change my period by multiplying by 1/3. So I'm doing a vertical stretch and a horizontal compression. So they did the vertical stretch first. So instead of going up to 1, now it goes up to 2. Instead of going down to -1, it goes down to -2. And so that just stretched it away from the x-axis by a factor of 2. And now we're going to look at multiplying x by 3. So instead of the low point being at pi, this low point being at pi, it's going to be at 1/3 pi, which is here. So this gets moved back to here. And 1/3 of this is pi over 6. So that got moved back to here. So it's going to cross here. So 1/2 got moved back to 1/6 pi. And 1/2 got moved back to 1/3 pi. And 3/2 got moved back to 1/2 pi. Wait a minute. No, 3/4 pi. So multiply by 1/3 again, so that's going to be 1/2. Let me look there. Over here. So this went to 1/3. This went to 1/3. And this one went to 2/3. Yeah. And that went to 1/6. And this went to 1/2. Yeah, I don't like the fact that they don't show the relative. They don't keep the same scale from picture to picture. That makes it hard for me to see, and I can only imagine what's going with y'all. So instead of going from 0 to 2 pi for the period, now it goes from 0 to 2/3 pi. So this whole thing got squeezed back to here. This got moved back to here. And 1/3. Yeah, 1/3 is here. That's right. And then 1/6. So Yeah, so this went down here like this. And that 3/2 went to 1/2. Okay. So now it comes down like this. Oops. Okay. So it got really squinched towards the y-axis. It got stretched away from the x-axis and scrunched towards the y-axis. I really wish they would do them in the same scale, so you can really see what's going on. The domain remained the same, and then the range changed from -2 to +2 inclusive. Okay, the period of a function is 2/3 pi, because the period is pi. The period of a function of a cosine is 2 pi, but you're going to multiply it by the 1/3. Oh, here they show it. They graphed it in a. I don't use this, so I just kind of ignore it until I saw what was actually there. Here is cosine. And here's our transformed function, where the highs go up to +2, the lows go down to -2, and everything's been moved this way. So this point is now here, this point is now here. This point got moved back to here. Actually, this point got moved back. Yeah, no, this point got moved back to here. This one got moved back to here. This one, I'll see where that one went. This one got moved to here. And this point here got moved to here. So the transformations of the trig functions, even I have some difficulties visualizing them. But it's not because I don't understand, it's just that seeing the pictures isn't always fun. Okay. Sine, and I already mentioned this, that sine and cosine are just a shift in the period. So I'm shifting the period 1/2 pi. Okay. So I'm shifting, that means I'm shifting this graph 1/2 pi to the right. So this point got moved over to here, this point got moved. No, this point got moved there, this point got moved there. This one got moved there. And this one got moved there. So the red was a cosine, the blue is a sine. Okay. If omega is greater than 0, the amplitude and period So the period is 2 pi divided by omega, so whatever omega is, you divide 2 pi by, and it gives you the period, which I use the letter T to for that variable. And the amplitude is the absolute value of whatever you're multiplying the function by. So previously we were multiplying by a -2, so the amplitude is 2. That means the highest it goes and the lowest goes is a plus or minus 2. Okay. So the amplitude is the absolute value of the coefficient of the sine. So that's going to be 5. So the amplitude is 5, and the period is 2 pi divided by what x is being multiplied by. X is being multiplied by, what is that, a 3? So the function, the amplitude is 2 pi thirds, 2 pi over 3. So A is 5, omega is 3. So the absolute value of A, which is still 5, is the amplitude. And omega is 3, so 2 pi divided by 3. Okay, the amplitude is 5, and the period is 2 pi over 3. So now to graph this using key points. Well, let's go through what they talk about with key points. Let's stand back here so I can read that top one. The amplitude is 2, and the period is pi. So everything got taken towards the y-axis by a half and stretched away from the x-axis by 2. Okay, so determining the step 1, do what I just did. The amplitude is 2, omega is 2, so the period is 2 pi over omega, 2 pi over 2, which is pi. So the amplitude is 2 and the period is pi. So for it to go through its full we're doing with sine. Okay, so sine goes through 0, 0. And at 2 pi and at pi, it's also 0. And at the halfway marks, it's going to be at 1 and -1. So what the amplitude does, it takes it the high up to +1 and the low down to -1. And the 1/2 means that this is going to be brought back to 1/2 pi. So now that 0 got moved back to here. And this 0 got moved back to pi. And so that means this amplitude here got moved back to halfway between. And this one got moved back to halfway between. And so now instead of going like this, it now goes like this. That should be here. And so now it's going to hit the y-axis, hit the x-axis at the half, every half pi. 1/2 pi, pi, 3/2 pi, 2 pi, 5/2 pi, 6 pi. 3 pi and on up. And so it's just been squished this way. And then at the quarter pies. No, this is, yeah. At the quarter pies is now where we hit our maximums and minimums. So if I ask you to do this on a test, this is what I expect to see. I mean, just do it just a little bit beyond one period, and what happens to that? And so and then this would be, this is y equals, what is it? 2 sine of 2x. Where this is sine of x. So because the amplitude is 2, the graph is between -2 and +2 on the y-axis. I already discussed that. And then because a period is pi, right? Then one cycle begins at 0 and ends at pi. And that's kind of what I did here with this. That's what I scoped out what happened to my max and min, what happened to my one period. It got cut in half. And then I looked at where my high points wound up and my low points wound up. Okay. Divide the interval into 4 units. Oh, that's kind of what I did, didn't I? No, I didn't do that. But that's what happens. Because we want to do those 4 units because each one of those, it takes us to the high, to the x-axis, to the low. So that's each of those 4 units, you're either hitting the x-axis or you're going to a high point or low point. And the 4 sub-intervals. So you have pi over 4. And then you have half a pi. And then you have 3/4 pi, and then you have pi again. Oh, okay, I see what they're doing. These are the intervals. They didn't separate them out better. So this is the first interval they're talking about. Here's the second interval they're talking about. And now this one is the third interval, and this is the fourth interval. Yeah, this should be up. Either this should be down here with this, or this should be up there with that. And they should put a comma between them or something to split them up. Okay, and so those will represent the key points. So the first, the y values of the key points go from 0 to -2 to 0. I mean 0 to 2 to -2 to 0 to 2 to 0 to -2 to 0 to 2 to 0 to -2 to 0 to 2. So yeah, so that bounces back and up and down again. And so to obtain those evaluated at each endpoint found in step 2. So yeah. So at the quarter marks, it's at its maximum or minimum. And at the half pi intervals, it's 0. Okay. And then you draw the curve. And actually, you would show it extending because we're not restricting the domain. Oh, they extended to that, okay. Additional key points appear at every pi/4 radian. Key points deal with maximum, minimum, and zero. So where's its maximum? Where are its zeros? Those give you your. And then when they throw in a horizontal shift, I mean a vertical shift, then that's just taking this whole thing and saying instead of going y equals 0, now y equals 3. And so y equals 0 is down here. So the x-axis got moved down in here. The graph ain't gonna change, it's just gonna change where it is vertically. So we'll get to that. So graph this, and I don't think we will, because I can't do that in a minute. So we're gonna start at this point, at this slide 130. Hope I remember. Okay. Any questions? All right, well, y'all are free to go then. I'll see y'all Wednesday. Hopefully,
Well-
things-
Will you post the PDF file to the files on Canvas?
yes.
Awesome. All right, well, you have a great day. I'll see you Wednesday.
Yes, take care. I'm going to end this, unless somebody has a question for me. All right, I'll see y'all later.